Hey everyone, it's your math teacher Mr. Boyden back at it again today, and today we're going to talk about dilations. Before we get into the math, where have you heard this word before? Have you heard of dilation, or some people say dilation? It's actually dilation. There's no A in front of the L, but where have you heard this before? Maybe you have heard it, maybe you haven't. The place I first heard it when I was at the eye doctor, and they would dilate my eyes. They make the pupil bigger so they can see deeper into your eye and to observe what's going on. And so in that context, they're going to make something change size, bigger or smaller. My pupil, it's a circle, and so it stays a circle when they dilate. It doesn't become squished or squished. It's still a circle, but it gets bigger and smaller. And that actually is a really good way to remember what a dilation is. It's when we're going to change the size of something. And you have seen this all the time, whether you've noticed it or not. So, like when I make a shape, I'm dilating it right now. Or if you've ever taken a picture and you've dragged from the corner, you're dilating it. Okay? I'm dilating the word dilation right now. I'm making it bigger and I'm making it smaller. Okay? So let's get into some definitions a little bit. There's two things that we need in order to perform a dilation. Number one is we need the center of the dilation, and we need a scale factor. And sometimes this will be called a dilation factor, but if you see the word factor, that gives you a pretty good idea. Now, do you remember where the word factor comes from or what it is? So we've talked about like sums, differences, products, quotients. A factor are things that are multiplied. And that's going to be useful in just a minute. And you can remember this phrase, dilation is multiplication. Okay? If you can remember that a factor is something that's going to be multiplied, this whole dilation concept gets a whole lot easier for us, and we're going to use that in a bunch of examples today. Now, going back to our first example, if I'm dilating this, let's try to understand a little bit better where the center is. So the idea is when I'm doing this, when I'm moving this back and forth, of course the point that I'm clicking and dragging is moving. What is the one point in this that is not moving at all as I make this bigger and smaller? Well, the word dilation is moving. It's up there, and then it's down here, and it's up there and down here. This corner down here, it's moving up and down. That's not the center. This corner up here is moving left and right. So where's the place it's not moving at all? It's right up here. That corner of the box, it's not moving in any way, shape, or form. So that's the center of dilation. It's like the point that's stuck in place. It was nailed down. It's not going anywhere. So that's going to be really important today. For the most part, we're going to be looking at graphs today. And the center is going to be right here. And so we're going to be stretching everything outward. Or maybe we're going to be pushing everything inward. So we're going to be crunching the shape down toward the origin or stretching it out away from the origin. One of those two. Okay, so let's get into it a little bit. Okay, here's our first example. We take triangle DIL. DIL. There's our triangle. That's a dilated version of the triangle DAT. So, chicken or egg question. Which triangle came first? The little triangle or the big triangle? We'll get to those questions in a minute. But what came first, the little or the big? If DIL is a dilated version, that means it came after. Okay, that's the big one. So the little triangle came first. So little triangle, and then it became the big triangle. So one way we could think about this as far as the center, is which point didn't move. We went from little triangle to big triangle. Do you know what happened to point A? Did it get stretched somewhere or did it stay in place? It actually gets stretched right down here. It moved, so that's not the center. What about point T? Did it stay in place or did it move? Looks like it got stretched down here to point L. So these points go whoop, and they get stretched down. So what point didn't move at all? D is still in its same place even when we draw this bigger triangle. So what's the center? It's the point that didn't move. That's D. Now let's talk about the scale factor. An easier question to answer than asking about the scale factor is how many times bigger is the dilated shape? And the answer to this is going to be a number. The scale factor is some number that we multiply by. So let's go back up and look at the picture, see if we can find any numbers to work with. Okay, and so I'm going to erase some of my writing a little bit because I overwrote this. And so what I'm noticing right now is this original triangle has a side length of 2. How long do you see this side length being? If you need to pause the video to think about that, please do. But I want to know how long that side is. Now the mistake a lot of people make when they don't take time to think is they say, 6, it's labeled, look, it's 6. But y'all, 6 is not correct. 6 is the distance from T to L. And I'm asking the whole side length of the triangle, all the way from D to L. Okay, so that would be 2 plus 6, and that would be 8. Okay, so I'm going to write this down here. The old shape had a side length of 2. The new shape had a side length of 8. How many times bigger is that? Well, some of you can answer that. You go, oh, I know the answer. If you can't answer that, here's how you think about it. We took the old shape, we multiplied by something, and that gave us the new shape. And so now we have a really simple equation to work with. And y'all, with dilations, that's as hard as they're going to get. I mean, there's fractions, but that's the equation. It's pretty simple. Okay, divide by 2, and x equals 4. So what we're saying then, how many times bigger is the dilated shape? It's 4 times bigger. So I'm going to look back up here, and yeah, sure enough, that big shape is about 4 times bigger. In fact, our math shows it's exactly 4 times bigger. Okay, that's our first example. Let's keep going. Let's try to find the scale factor on this one. Now, after our previous example, I'd like you to pause the video, write this down, and I want you to try to answer the question on your own, and then I'm going to point out a little detail about it. But pause the video now and try this one to see how you're doing. Do a quick check for understanding. Okay, what I see right here, the old shape, oops, I spelled old incorrectly though. Redo, this is why I teach math. Old shape has a side length of 4, and the new has a side length of 12. And so my scale factor is 3, because 12 is 3 times bigger than 4. Or 12 divided by 4 is 3. Now one thing I want to point out, how do we know which shape is the new shape and which shape is the old shape? Because isn't it possible that this big shape was the old shape and then it shrunk down? Yeah, that is possible. Here's how we can tell the difference. Notice right here, this R, you see how it has an apostrophe after it? The way we say that is prime. Okay, make sure you're marking this down in your notes. The way we say that is prime. So R was right here, R prime is right there, and prime means it's the new point, or they call it the image point. Okay, so that is the new point. The one that does not have the prime, R, that's the old point. Okay, here's T, and then we get T prime. Prime is specifically saying, I'm the new point. I was changed to become here. I was not originally here. And then down here, look at this. X is in the same spot. So they're saying X prime equals X. They're saying that's the same point. What would we call that? What's the vocab word for the point that doesn't move? Ah, the center of dilation. Okay, let's keep going. All right, let's do a little bit of graphing. Alright, and so this is a normal question that'll come up. You'll be asked to graph something and you'll explain what the answers to the questions are. Triangle TRA has vertices of 2, 0, and make sure you label it as T. R, 0, negative 3, R, and A, negative 2, 1. T, R, A. And it's a triangle, so I should make it look like a triangle. You may want to pause and make your image look nice on your page. Give the image of the triangle. After a dilation with center at 0, 0, okay, 0, 0, the origin is the point that's not going to move, and a scale factor of 2. Now remember, dilation is just multiplication. And so what I'm going to do is I'm going to take all these points. So I had 2, 0, and that was T, and I've got 0, negative 3, and that was R, and I'm running out of space, but A is negative 2, excuse me, positive 1, negative 2, positive 1. And what I'm going to do is I'm just going to multiply all of them by 2. So times 2, times 2, times 2. Now this relates back to algebra really, really nicely, because all you have to do is distribute this in. Distribute, distribute, distribute. Looks like I forgot my comma. Okay, and so now what we have, I get T prime, the new point, and that is 2 times 2, which is 4, 0. Now look at this. 1, 2, 3, 4. So that point moved away from the origin, and I'm going to call it T prime. Okay, I'm running out of space for R, so I'm going to bring that down here. I get R prime, and that now equals multiplying into 2 times 0 is 0, 2 times negative 3 is negative 6. And so that's my new point, R prime. So negative 6, so down 1, 2, 3. Okay, and I'm going to call that R prime. We want to label this so we know what's what. Okay, and then one more. It looks like I have room for A right here. A prime is going to be multiplied by 2, negative 4, negative 2. So left 4, 1, 2, 3, 4, down 2. Hey, it's right in there. Okay, so that's A. Oh, excuse me, I made a mistake. Do you see my mistake? I actually just realized that was an honest mistake. Okay, I made a mistake here. Negative 2 times 2 is negative 4, but 1 times 2 is positive 2. Okay, so that was a mistake. Let's fix that. We all make mistakes, don't we? So left 4 up 2, and that's now point A prime. And so now I'm going to connect my dots. So look, it's the exact same triangle, it just got stretched to be twice the size. And so now we have our new triangle. Now we're going to go to the next question. I'm going to have to erase this because I'm out of room. We want to do the same thing, but now the center is 0, 0, and the scale factor is 1/2. So we're still just multiplying by 1/2. And so that's not going to be super, super hard. I'm going to take those points again. I'm going to take T and R and A. And it's still 2, 0. I'm using the original points, not T, R, and A prime, but just T, R, and A. Okay, so 0, negative 3, and negative 2, 1. And this time, we're going to multiply by 1/2. That's what it says to do, so let's do it. Okay, let's see what we get. We get T, I guess you can't call it prime, because we already have T prime on here. So you can't do that. What we could do, though, is call it double prime. Okay, that means it's the next set of points. Not prime, it's the one after that. Okay, 1/2 of 2 is 1, 1/2 of 0 is 0, so I get 1, 0, and I'm going to use an arrow. That's T double prime. Down here, let's multiply. I get 0, and that point is R double prime. So I get 0, and then 1/2 of negative 3 is negative 1.5. So on our graph, we're just going to go down 1 and 1/2. Okay, that's R double prime. And then down here, multiplying by 1/2, I get A double prime. 1/2 of negative 2 is negative 1. 1/2 of 1 is 0.5. Oops, too much. Okay, let's graph that. Left to the 1, or left 1, 1/2 up, and there's my new little shape in there. Okay, so one thing I want you to see, when this number is smaller than 1, the shape gets smaller. 1/2 is smaller than 1, and we've got a smaller shape in there. When that number is bigger than 1, it grows, it gets bigger. The shape gets bigger. Okay, so keep that in mind. That can be kind of a quick check in case we ever start to make a mistake on this. Okay, let's try another one. Okay, on this one, a triangle has vertices of 0, 0, 0, negative 5, and 7, 2. Oops. And I'm going to put the letters on there. A, B, C. They want the vertices of the triangle after a dilation with center of 0, 0 and a scale factor of 3/5. Remember, dilation is multiplication. So, let's take our points. 0, 0. Oops. That was A. Redo. A little sloppy. A kind of looks like a face. B, 0, negative 5. And C, 7, 2. Now, why don't you pause the video and try to predict what I'm going to do? In fact, why don't you try it? It's like when I ask you in class, would a good teacher do this with you, or would a good teacher give you a chance to try it on your own and then support you as you work? So guys, I want to give you the chance to try it first and then be supported. So try to decide what we're going to do next, actually execute it, and then play the video and check your work. Okay, here it is. So spoiler alert, if you haven't paused, you need to pause. Okay, so here it is. If you have a 3/5 right here, and that is a scale factor, you need to multiply by that. So times 3/5, and times 3/5, and times 3/5. Okay, here we go. 3/5 times 0 is 0. Okay, that was kind of boring. So A prime and A are the same. That actually makes sense. That's at the center. And so, yeah, of course it didn't change. That's the point that doesn't change. That's one of the ways we defined it. So that's A, and that's also A prime. Let's go to the next one. 3/5 times 0 is 0. Okay, that was easy. And 3/5 times 5, you can use a calculator if you need, but look, 5 on top, 5 on bottom, they're going to cancel, so this is negative 3. 0, negative 3. 1, 2, 3. Now, it looks like the shape is shrinking, because B moved closer to the origin. Why is that happening? What's happening with 3/5 that's making this shrink rather than grow? Well, look, 3/5 is smaller than 1. That's always going to make it shrink, okay? Let's go to the last one. Okay, here we have 7 times 3. That's 21 fifths. Ooh, interesting. And then we have 2 times 3 is 10. Excuse me, is 6. 2 times 3 is 6. So that would be 6 fifths. I think I did 2 times 5 in my head on accident. Sometimes we do that. Okay, so let's get this written out. C prime. And now, maybe it's easier if we turn those into decimals. That'll be easier to graph it. So 21 fifths turns out to be 4.2. And 6 fifths turns out to be 1.2. So let's graph those. 4 to the right, 1, 2, 3, 4. 0.2 means go just a little bit more. So 1, 2, 3, 4, then a little bit more. 1.2 is 1, and then a little bit more. And so there it is. There's C prime. Okay, and there it is. Now notice, that looks really similar to some of the examples we've done, where we have a smaller triangle and inside, and we have that bigger triangle stretched down. That looks an awful lot like our very first example we did. Okay, so we've looked at it when it's given, and we've now created our own visual that looks like that, and we've seen what circumstances lead to a picture like this. Okay, now let's do one without the visual. Okay, we've used the visual, we've seen it, we also want to be able to do it even if we don't have time to graph it. Okay, so we get a point 3.2, dilated with a scale factor of 4 and a center of 0, 0. What is the new point? Pause the video and try it yourself. Multiply by 4. 4 times 3, comma, 2. That's 12, 8. Boom, done. Guys, that's all it is. Dilation is multiplication, okay? Dilation is multiplication. Dilation is multiplication. Okay? What if it was dilated with a scale factor of 2? All right, if you got that one, congrats. Way to go. If you didn't get this one, shot at redemption. Pause the video, try it. 1/2 multiplied by 3, comma, 2. Equals 3/2, comma, 1. If you also wrote it like this, 1.5, comma, 1, I would totally accept that, okay? Both of these are excellent answers. Okay? And let's do a couple more visual, and then we'll be done for today. Okay? For this one, we want to give the coordinates of the image. Wait a minute. Is the image first or second? Hold on. We talked about old and new before. Old might have looked like something like point A. New would have been called A prime. This is also called a pre-image. And the new one is called the image. Okay? So maybe you want to add this chart to your page so you can see which things go together. That'll help you with the vocabulary a little bit. Okay? So the image means the new one. This is the old one. That's the pre-image. Okay? After the scale factor is applied. And we've been given a scale factor of 3. Okay? So when they say coordinates, they're not asking us to graph it. We've been given a picture. We're going to use the picture, but we're not being asked to graph it. The only reason we have the picture is so that we can find the coordinates of the old image, the pre-image. Okay, and so I'm going to do that. The points on here are called Q, P, and R. And we're going to need the coordinates of those. So let's see. P looks like we go 2 to the right and 1 down. So 2 to the right, 1 down. R looks like we go 4 to the right and 1 down. And Q looks like we go 2 to the right and up 1, 2, 3, 4. All right. Scale factor was 3. What are we about to do? Because anytime you feel like you can finish this, pause the video and try it. Or try racing ahead if you feel comfortable and see if you can do this. If all you ever do is watch, it's going to be harder for you to learn. You have to actually engage with it. Okay, so all I'm going to do is multiply these by 3. And that's going to tell me that the coordinates of Q prime are 6. And 4 times 3 is 12. Okay, so I've got the coordinates of Q prime. Coordinates of P prime, let's multiply them. 3 times 2 is 6. And 3 times negative 1 is negative 3. And let's find R prime. R prime multiply in, so we get a 12. And 3 times negative 1 is negative 3. Let's double check and make sure we answered the question that was asked. Oops. They said, give the coordinates of the image after the scale factor is applied. Okay, so I took the coordinates, I've applied the scale factor right here, And now we have the new coordinates. So I'm going to box those off to demonstrate that I understand that I've answered the question, and we're done. Okay, we got one more. I'd like you to do this one on your own. Okay, I think you can probably handle it right now. So we've got an image on the screen, pre-image rather. We've got a scale factor of 10 and the same prompt. Give the coordinates of the image after the scale factor is applied. So pause the video and try it. Okay, and I'm going to start working on it as well. So for R, it looks like we have 1, -3. For P, it looks like -5, 1. And for Q, looks like -1, 2, 3, up 1, 2, 3. So -3, 3. This says to multiply by 10. Piece of cake. Multiplying by 10 is easy. We got this. Okay, and so now we're going to get our new coordinates. P prime, Q prime, R prime. Here we go. Multiplying by 10 all the way through. 10 times -5 is -50. 10 times 1, 10. 10 times -3, -30. 10 times 3, +30. 10 times 1, oops, 10. And 10 times -3, -30. There's the coordinates. So y'all, here's what I'd like you to see. A lot of times it's really tempting to graph it because many of us are visual learners. In fact, most people learn best visually. I totally understand that. I'm a visual learner, okay? However, if you had to do this visually, you'd have to spend time retooling these axes in order to be able to fit 50 on there. And you'd be spending extra time thinking about that. You'd be spending extra time drawing. And if you didn't do that, then you'd need a massive sheet of graph paper. It'd have to be huge. Like you'd have to stitch 3 or 4 pieces together. Okay? And so what we have here is a way of doing it that's quick, and it's not necessarily harder than graphing it. In fact, it's a lot easier than graphing it when we have big numbers like this. Okay, so that's our dilation video. Hope you enjoyed it. Good luck on your assignment. We'll see you next time.